There's an old Jewish proverb that says, you cannot be a prophet in your own village. And at the University of Maryland, especially computer science, they take it very seriously. That is why they are not hiring their graduates, except in exceptional circumstances, like for Professor Regia, who retired last year. Now, Katie Skinner, she grew up in Long Island, New York, and she did her undergraduate studies at Princeton University in mechanical engineering and aerospace engineering. And then she moved to the University of Michigan, where she did her master's degree and PhD dissertation. Afterwards, she went to Georgia Tech, where she had a research appointment in a number of institutes. And after that, she returned to the University of Michigan, where she got her PhD, where she is now an assistant professor. So you can understand how exceptional Professor Skinner is. And today, we are very happy to see her research on machine learning for robot perception in the wild.
Thank you very much. Oh, this is a little bit loud. Oh. Can everyone hear me if I turn that off? Okay. Hopefully that's okay for the recording.
Well, I think for the streaming, we do need you.
Oh, you do need it?
Yeah.
Do you know how to turn it down slightly?
Maybe if you just move the microphone slightly.
Okay, I'll try that. Yeah. Okay. Well, thank you very much for that introduction. It's been really great to be here to see all of the work in robotics here and visit a couple of the different labs. I'm really excited to talk to you today about my lab's research and our work in machine learning and robot perception for field robotics. So field robotics spans a lot of different applications and environments, anything from air, land, sea, and space. Really, anytime we're putting a robot in a challenging outdoor dynamic environment, we refer to this as field robotics. And there's, of course, a lot of operational challenges with deploying robots in environments like this, but there's also a lot of kind of theoretical challenges that we still need to overcome before we can see truly autonomous vehicles working in these spaces. So today I'm going to talk to you about some of the challenges my group has been thinking about, especially pertaining to machine learning for problems in robot perception. So first we're going to start with marine robotics, an application that's near and dear to my heart because I've been working on this since the beginning of my PhD. And marine robotics is a really exciting field. So it allows us to explore anywhere from our Great Lakes to our coastal regions, all the way to the deepest parts of our oceans, and maybe someday in the future to future missions on Europa and ocean worlds. So it's a really exciting domain to be working in, but of course comes with a lot of challenges, right? When we deploy robots in underwater environments, we have to take a lot of considerations for the environmental conditions that we're working in. And these can be pretty challenging. On the perception side, we have a lot of challenges to traditional sensors that we might be used to working with in robotics, like cameras and LiDAR sensors. LiDAR is less efficient underwater, and cameras do not work well at long ranges, so we turn to other sensors for carrying out marine robotics missions. So one sensor I'm going to talk about today is side-scan sonar. So side-scan sonar is an acoustic sensor that's a very valuable sensor underwater. It allows us to carry out long-range survey missions to capture relatively high-resolution information about the seafloor. But I want to take a minute to kind of talk through what side-scan sonar imagery looks like so you can understand how different it is from what we're used to seeing on land. So on the left, we have an illustration of an AUV, and the side-scan sonar has two lenses, one on either side of the vehicle, that goes out in kind of a swath pattern on either side. So on each side, we have half a swath width, and in the middle, right underneath the vehicle, we have what's called the nadir, where we don't actually get any information. It's kind of a dead space in our image. So you can see that we can capture some pretty high resolution detail This is an image of a shipwreck that we captured in Lake Huron on one of our missions. So it's a very powerful sensor. We can see long range, capture pretty good detail, and it's small enough to be integrated onto autonomous vehicles, even vehicles that are about a meter length in size. And here's an example of another image that we captured in Lake Huron. So this is the Monrovia shipwreck, and you can see we have, I think, about 130 meters on either side that we're capturing. So the full width of this image is 230 meters, which is, or I guess 260 meters, which is pretty impressive. So if all of our side scans and our images looked like this, I think our job would be pretty easy, right? Even as non-experts in this room, I think you can tell what we're looking at here. But the case is that really not all of our images come out looking this clean. And there's a lot of challenging effects that we actually need to think about and overcome when we're working with side scan sonar data. So here's an example where maybe we had not as clean of a pass over a shipwreck, and you can see that we have a lot of noise and distortion on this object. It's a little bit harder to make out what we're looking at. You can also see some of these interesting kind of shadowing effects that we get because we can't actually see anything behind where the sonar ping returns, so there is some dead space in the image as well. And in general, dataset collection is very expensive, and it's difficult to capture instances of rare objects like shipwrecks. So any objects that we see, of course, are relatively sparse in terms of the full data set that we're collecting over the full survey mission. So we can see a couple of other kind of negative effects. So you can see this image we may have captured a little bit too close to the surface where we have wave conditions, so you can see some of these noise effects. And in some cases we have pretty clean images, but just from the complexities of shadowing in sonar images, it's still a little bit difficult to make out what we're looking at in the scene. So here, I don't know if anyone spotted it, but there is a shipwreck in this scene as well that maybe if you didn't know where to look, you might not have noticed. So this inspired us to think, we're planning to send out AUVs to collect large area surveys of underwater environments. This can return many gigabytes of data that typically marine archaeologists would manually search through, find potential areas of interest, and then do repeat surveys to confirm those areas of interest. Our goal instead is to think about, can we actually teach robots to automatically detect shipwrecks so that someday we could just send these robots out and they could find potential objects of interest, maybe replan to survey them closer without having to do this expensive replanning and manual searching that we're doing right now. So this led to one of my first projects, which is funded by NOAA Ocean Exploration, to look into machine learning for automated detection of shipwreck sites from large area robotic surveys. And the first goal of this work was, of course, to develop the machine learning methods to actually automatically detect shipwrecks. The second was, once we had initial detections, can we enable robots to perform autonomous close-range surveys of shipwrecks to actually collect RGB images of these sites? And then the third, because there are a lot of challenges in marine robotics with having accessibility to the data that we're collecting. It's expensive to collect this data, and it's not always widely shared, so we did want to make it part of our mission to increase accessibility of this data collected, to put out an open source or publicly available data set for others to work with on this problem. So this led us to Thunder Bay National Marine Sanctuary. So this is the northeast coast of Michigan that you're looking at in Lake Huron. This sanctuary is jointly run by NOAA and the Michigan State Department, and it's a very unique site because they have 100 known shipwrecks in this local area and 100 suspected shipwrecks. So this was a very popular shipping and transportation channel in the 1800s when they had maybe less accurate navigation radio communication systems than we have now, and this led to a lot of wrecks in this local area. So it's a really unique area for us to carry out this work because we do have a lot of known sites that we can visit to collect data for maybe training and testing these methods that we're developing. So the overview of our process looks something like this. We initially would plan a lawnmower pattern mission for our AUV, deploy the robot to some known site, collect imagery, input that image to our network, our trained network, and then hopefully output a detection of that shipwreck image. So I'll walk through each of these steps in a little bit more detail. So for these missions, we're carrying out lawnmower surveys, which are pretty typical for AUV surveys. And essentially, these allow us to predefine our survey path so that we can collect the survey data that we're interested in. One challenge with underwater vehicles is we don't have access to GPS, and we have very limited communication while the vehicle is underwater. So to get around this, we plan in some points in our survey where we're going to surface, get GPS lock, and that will allow us to correct our survey path when we dive back down for the next survey, so we can make sure that those survey lines are really tight and have the overlap that we need for our mission.
How long is the time underwater? When you come back, what is the time span for that typically?
Oh, well, it would depend on the depth that we're going to. So most of our missions were probably around 45 minutes to an hour, but we did some that were about 2 hours long. So yeah, it really can change depending on those operational parameters. And even though we're setting predefined paths here, there's still a lot of design choices that we have to make. So we need to consider things like the survey area, how long the mission's going to be, spacing between legs, swath width, and altitude or depth. So we were working really closely with the marine archaeologists at the sanctuary to help set these parameters, especially when we were working in and around the wrecks, right, to make sure that we weren't going to interfere with any of those historic sites. So once we have these pre-planned missions, we deploy the Iver AUV for its search mission, and once it's underwater, we have very limited, we have no communication with it unless it's on those surface points where it might send us a message with some updates. And then when we get it back on board, we look at the data, and it might look something like this. So this is a side scan image, and this is shown in a waterfall pattern because it shows us line by line of the sonar pings that are going out on either side. And you can see there's a couple of interesting features in this image already. We do have a shipwreck here. This is barge number 1, which we called the chicken barge because it sank with a boatload of chickens that all washed ashore. All of the wrecks, of course, have very interesting stories behind them. So this is, what we might see when we return our data to the boat. And when we get back on shore, we worked closely with marine archaeologists to actually help label this data so that we could investigate machine learning methods for automatically detecting the shipwrecks. So we labeled not just the shipwreck itself, but we also labeled the debris field around it, which would be contained in the wreck site, and then also maybe some man-made structures like mooring buoys that NOAA places out to mark the sites around the bay. So maybe just one cautionary tale. For the most part, I would say our fieldwork went pretty smoothly, but of course you never know what to expect when you're deploying robots in the water. So on the afternoon of June 2nd, we deployed the Iver to survey the wreck of the Puwabik, which is a very important wreck in the local area because there was a large loss of life for this wreck. So we went to survey this wreck. About midway through the mission, about an hour in, we received a distress call from the Iver indicating that there was a leak. The Iver does not have any planning capabilities, so what it does is it executes a safety response plan if it can. It tries to go back to essentially the waypoint that we told it to wait so that we could come and pick it up. This is what we saw when we got the vehicle back on board. So for some context, this is the side scan sonar lens, and what you're seeing is the lens itself had been slightly detached from the lens mount, and that was enough to spring a leak. Luckily, by the time we got to it, it only had a couple of drops of water in it, so that was pretty lucky, but even this minor damage can cause the quick end to any of our field work for that expedition. Does anyone have any idea what might have caused this? We don't have any sharks in the Great Lakes, so it's not any wildlife. Yeah.
Bump into any rock or something?
A rock? No, it wasn't a rock. There's not too much structure down there, actually.
Pressure?
What's that?
Pressure?
Pressure? No, luckily not. The actual culprit was a mooring buoy. So as I mentioned, NOAA marks its sites with these mooring buoys. Most of them are marked or held by rope, but because this site is so important for them, they actually have some submerged mooring buoys that have steel cables attached. And we had, talked to the archaeologists beforehand, and they said, there isn't much relief on this site, but the only thing you need to be aware of is there are some steel mooring cables, which we had marked on GPS, and we weren't, too close to them, we thought, but they can drift underwater. And, what are the chances that you're going to, in the span of a 2-hour mission, run into a centimeter-wide line?
Is it like a teleoperated, or there's a motion planning? Isn't there like a motion avoiding algorithm used?
So there is a forward-looking sonar that can detect some obstacles. I would say it's most successful at detecting when you're starting to run aground, because it's a pretty sparse measurement that we're getting back from it. So ideally, yes. And if anyone's working on this, let me know. But it's a problem with both kind of the sensing resolution that we have, and then also that it isn't really going to do any replanning. It will just start to abort the mission.
And you're relying on your inertial sensors primarily for doing the navigation?
Yeah, we're relying on the DVL and the IMU. Yeah. We did get the data back from this vehicle, and it's pretty interesting. So you can see as the vehicle was traveling, it maybe got stuck on that line and swung around a couple of times before it freed itself. So, things don't always go smoothly. Luckily, they were able to repair the vehicle, so we could use it again the next year. But always things that happen. So we spent about 5 weeks over the course of 2 years up in Thunder Bay, and we were able to capture sonar imagery of 29 sites. At a range of depth, the deepest site was about 80 meters deep, and the site length would be the size of the boat. So most of these boats are pretty large, but we had a couple of smaller ones around 24 meters long, and different materials, different terrain types. So this was a very useful data set for us to try to evaluate our machine learning methods. There have been some prior work in segmentation from side scan sonar that specifically tried to detect the unique shadow patterns of objects with high relief in sonar images. This can still be challenged if you have complex terrain that maybe throws off a couple of those shadow patterns already. And the other challenge just practically is that these methods were trained on manually labeled data, which even with 29 sites, if you're splitting into a training set and test set, you have very limited number of sites that you're actually going to be training on. So we decided to look at a slightly different problem. We actually have a large amount of publicly available sonar data of general terrain, and the challenge really is just that the objects that we're interested in are so rare that we have a limited amount of labeled data for training our methods. So we actually asked the question, can we detect shipwrecks without seeing any real examples during training if we have access to a large amount of general terrain data? And for this, we incorporated kind of two different ideas. So one is simulated data, and the other is the idea of anomaly detection with deep learning frameworks. So we framed this as kind of a targeted anomaly detection problem, but really it's zero-shot semantic segmentation for real shipwreck examples. So for our training data, we have synthetic data that we're generating that combines both real terrain examples and simulated shipwrecks on top. And then we have our sim-to-real transfer network that's going to be able to predict shipwrecks in testing. And we found that this kind of targeted anomaly detection that's guided by simulated examples actually does pretty well. So rather than we're comparing it to examples that only perform sim-to-real without having any sim-to-real transfer, those completely fail. Even methods with some sim-to-real transfer have challenges as well, but our method can perform generally pretty well. So here's an example of some of the simulated images we're able to generate with our simulator. So as I mentioned, the terrain, the actual background terrain is real bathymetry or real side scan sonar data that we have public access to from NOAA databases. And the simulator we developed was based on Blender, and this allowed us to superimpose the simulated side scan of shipwrecks onto the real terrain data. So with this, we have some labels for the simulated examples, but we're not training on any real examples of ships, which allows us to save all of our data for evaluation. The network itself, as I mentioned, was inspired by anomaly detection frameworks. So it's a student-teacher network where the student network is looking at the synthetic image of the shipwreck, and it is first trying to detect anomalous objects in the general terrain versus the terrain with synthetic shipwrecks, and then it will try to investigate whether that shipwreck is close to the examples of the synthetic shipwrecks that we actually care about. And there wasn't really another method that was approaching this specific problem, but we compared to a wide range of methods, both in deep learning for anomaly detection, in domain adaptation, and also in side scan sonar image segmentation. And if we train all of these methods with no real examples, so only with the simulated examples that we have access to for our training, we see that our method outperforms this range of methods. So we hope that with our data set, others can investigate this problem as well, or maybe other problems with shipwrecks for machine learning, and that it can lead to some more advances in the field. So here's just some qualitative examples. So again, the ground truth was created working closely with marine archaeologists to hand label all of these images, which my grad students really enjoyed doing. And you can see that our method, STARS, comes pretty close to those ground truth images. But we do have a couple of failure modes. So I would say, in general, there's a couple of hard problems, especially when we split the shipwreck, knowing which sites are shipwreck or not shipwreck. And this example on the bottom is actually not a shipwreck, but we detect it as a shipwreck. It's an artificial reef that lies in kind of a linear pattern, so may look in feature space like a shipwreck, and you can see we have kind of a false detection on this. So one thing we're interested in looking at in the future is how to reduce that false detection rate so that we can make sure that what we are detecting is a true shipwreck. So we tested this when we went back for fieldwork this past year. These are all of the known sites in a pretty small area, probably about an hour and a half long boat ride maximum out to these sites. And we went to a couple of different sites and were able to, with our trained model that hadn't seen any real shipwrecks, detect shipwrecks that we had visited for the first time. So it was pretty exciting to see. And while we're not doing this detection on board the AUV, we're able to run it on a laptop on the boat in under 5 minutes, which could save a lot of time, even compared to taking the data back on land to be analyzed by archaeologists. So this was a large collaborative project, and we worked with collaborators at LSU who were interested in using the output of our detection method to plan for close-range imaging surveys of our shipwrecks. So from our detected sites, you can see we did some kind of smoothing of the contour to make it more amenable to path planning methods, and then our collaborators developed a method that would plan a path to do close-range imaging surveys of this mission. So we had a couple of other underwater vehicles with us on this expedition. These are two kind of custom AUV vehicles, and they're based on the Blue Robotics platform, Blue ROV platform, if you're familiar with that, but with a couple of extra sensors on top. So the ROVs are named Bruce and Dory. Nemo came the first year but didn't make it the second year. Dory has stereo cameras facing downwards so that we can collect imagery for making 3D reconstructions of these sites. And Bruce has just the monocular camera forward, but had a couple of other sonar sensors for collecting sonar imagery. We deployed these ROVs for imaging surveys and, of course, need to monitor them, or we have the tether access so we can monitor them during the mission. But the ROVs themselves were able to carry out fully autonomous surveys of a couple of shipwreck sites at pretty close range. So this is a video from one of the autonomous surveys of a shipwreck site. If I left the volume on, it's pretty loud, but so this is the Monahanset site. It's relatively shallow, but it has some pretty interesting features. And from the images that we collect from these autonomous ROV surveys, we're able to create large-scale 3D models of these sites, and this is something that would be metrically accurate that archaeologists could use to analyze the changes in sites year after year. So currently they do manual surveys where they take images themselves and then they look through the images from one year to the next and try to compare differences. We're hoping to move towards better automation to do this, to both collect the images in a very repeatable format that you're getting them from the same location year after year, and then eventually could perform automatic change detection on them as well. So, practically I think this was a success, but it also, of course, inspires future work based on some of the challenges that I want to point out. So one is that this 3D reconstruction is developed offline, and there is some color distortion because we're not doing any color correction on these images. In general, 3D reconstruction underwater is pretty prone to holes and sparsity and prone to artifacts, which you can see a couple artifacts in this image as well. So we have been working towards improving this to improve our 3D model reconstruction for underwater scenes. I want to talk a little bit about the challenges of 3D reconstruction underwater. If you haven't worked with underwater images, this is usually what people think of. So brightly colored coral, brightly colored fish. As we saw in that first image, this isn't quite what it looks like. And one challenge is that from one environment to another, things can appear quite differently as well. So even from this video to the last one, you can see we have a totally different color cast on this image, and that would be because we have different attenuation parameters in this environment. But in general, we can see about 2 meters in front of us is the typical survey range that we set for marine robotic platforms. And we can look to the physics of underwater image formation, why this occurs. So as light travels between the light source, camera, and the scene, interacts with particulate matter in the water column, which leads to attenuation and scattering. Attenuation is wavelength dependent, so this means that for each color it's going to lead to degradation at different rates. In most ocean environments, we see the red channel attenuate much more quickly than the blue and the green channel, which is why we see more blue-green images in most ocean environments, but you can also find environments where you have more of a reddish hue as well. So it really depends from one environment to the other. So attenuation leads to this color cast, and then backscattering is very similar to fog in air. So as you get further away from the camera, you see kind of more of this haze or fog effect as well. And both of these effects are range dependent, which has pretty important consequences. So as you get further away from between the camera and the scene, you're going to see a more extreme distortion due to these effects, which makes it difficult for us to reason about them. From a computer vision perspective, this leads to several challenges. So one is feature detection and matching. In air, we typically rely on having high contrast image patches. So this is an image patch or a couple of image patches from an artificial rock platform that we took images of in air. And then we submerged that same platform and found the same image patches, and you can see the difference in contrast that we have just from our in-air images to our underwater images of the same feature. So this makes it really challenging to perform feature detection and matching. And then we also have a breakdown of photometric consistency. So for direct SLAM methods, we use this idea that if you are imaging a feature from one location and you move to a slightly different location, there's going to be some consistency in how that color appears in our image. But for underwater imaging, this assumption can break down. So as you move from one view to another, because all of these effects are range dependent, sometimes viewing angle dependent, we don't have this notion of photometric consistency underwater. So this means that it's very difficult to use direct SLAM methods without doing any pre-processing underwater. So what we've been looking to in recent years is some potential new opportunities to overcome some of these challenges. I've worked a lot in image restoration, and one thing I'm really excited about in this space is the advance of neural radiance fields. So if you're not familiar with kind of the explosion of neural radiance fields in the computer vision field, essentially NERFs take multiple images of a scene and they learn a dense volumetric scene representation. So they actually learn to map from camera camera position and viewing direction to coloring density of scene points. And this can be really powerful. It can enable novel view synthesis, so you can render views that were unseen during the actual data collection, and it can enable us to get dense depth estimation of the scene as well. So we have started looking at how we could use NERFs for underwater scenes. Our kind of initial take at this was using a general NERF off the shelf. So the initial depth estimation and novel view synthesis is just from the MIP NERF backend. But then with this initial depth estimation, can we use this to estimate the attenuation parameters that would be needed to get consistent corrected color of our scene? And then during test time, once we have a trained model, we can render any position and viewing direction and output the dense depth and the corrected color image as well. So this was kind of early work using or trying to leverage NERFs underwater, and I think there's a couple of promising things that came out of this. So one is we were really excited about the density of the 3D reconstruction that we're able to get from these methods. It's really difficult to get dense depth maps underwater, whether it's feature-based methods or direct methods. So I think we're really excited about the potential for NERFs to allow for dense 3D reconstruction, and this can really help with recovering consistent corrected color as well. So just from a single view rendering the depth and the corrected color, we're actually able to project that into a pretty accurate 3D model of this small scene. But just to show that we have limited holes, limited artifacts, and this can lead to a much more useful 3D model in the end. So we're really excited about NERFs moving forward because they can learn this dense representation, and there's potential to incorporate the model of underwater image formation as well, so that it can actually learn to correct for those effects. But a couple of caveats here. We're still training offline. I think NERFs are really powerful, but there are a lot of questions on how to make these practical for robotics applications. And for this work, we required images from multiple viewpoints, which we don't always have from our robotic surveys. Very often we're traveling in kind of a straight line as we're navigating to our goal. We're not necessarily doing 360 surveys around each object that we're looking at. And then lastly, in kind of the early days, these were challenged by large unbounded scenes. So we're interested in, recovering all of these kind of disadvantages in the underwater space, but I want to talk about some of our work we have been doing to improve NERFs for another application on land, autonomous driving applications. So there's a lot of perception problems that have maybe been considered solved in autonomous driving, but I think there's still a lot of challenges that we have to work with, right? So in many scenarios, we have pretty sparse, noisy data, or the visual appearance of images that we're looking at can change from one season or one day to the next. So these are some of the challenges that we've been thinking about for autonomous driving applications. And our first stab at this was something called Cloner. So the goal of this work was to overcome that challenge that we need that 360 view for NERF frameworks to learn a dense model of the scene. And the goal of this was to take a single input stereo image and a single LiDAR scan and see if we could learn a dense reconstruction from just those two starting points. So this would be the scenario where you have your robot maybe in initialization where it needs to quickly learn how to model the scene. And then at the output, we can perform novel view synthesis and also dense depth reconstruction as well. So kind of the main insights for Cloner that helped this all work was the first step that we did was we used the LiDAR data to learn a 3D occupancy grid, and we used that learned 3D occupancy grid for our sampling to prioritize sampling around occupied space. The second thing that made this work was that we separated the learning of RGB and LiDAR depth data. So we had decoupled the training from camera and LiDAR rays. The LiDAR rays used that learned occupancy grid for sampling and learned to output the depth, which we used for the depth rendering. And then the camera rays were, again, using that same shared occupancy grid for sampling, and then learned to output the color only. So this was kind of our approach to achieve sparse sampled views for NERFs with RGB and LiDAR. And you can see there's some regions that break down, especially at the edges of the camera image, or well beyond the camera image. And then also the sky, I would say, is a challenge because we didn't have LiDAR returns in that area for the depth map. But in general, we're able to recover pretty fine features, and we're able to see a smooth reconstruction over the road area, some of the more featureless areas of the scene. So we're pretty happy with this depth completion result and our novel view synthesis capabilities.
What is that region towards the end where the orange region is there?
What's that?
What is the range of his LiDAR that you have typically? And what is that orange region that I see there towards the end?
Oh, that is the orange at the end?
Yeah.
That's just the farthest distance. So I think we're just scaling for visualization. This is actually from the Kitty dataset. So I'm not sure exactly what the range is. But yeah, the noise in the middle is from mostly the sky.
Thank you.
So this work showed that we could handle sparse viewpoints for learning implicit representations of scenes. We could handle varying lighting conditions because of this fusion of LiDAR and RGB data. And we could operate mostly in unbounded scenes, although, again, the sky region is still a little bit for future work. But the main limitation here is really we're still training offline. So for robotics contexts, this is something that we need to overcome so that we can actually use these methods on board our vehicles during our missions. So this led us to our next work called Loner, which allows us to perform real-time SLAM with neural representations using LiDAR only. So we started with LiDAR only because this helped reduce the computational complexity of RGB rendering. But we approached this problem in that we really wanted to achieve real-time localization and mapping with implicit representations to see if this was feasible for LiDAR that would be actually on board a robot or an autonomous vehicle. So the method takes in LiDAR scans, and we have a kind of traditional SLAM framework where we have separated our tracking and mapping streams, and the tracking uses ICP alignment of sequential LiDAR scans. We are performing some motion compensation, and we are sampling those sky regions so that we can ignore those where we have noisy measurements. And then the mapping sequence is where we're actually performing the training for the neural implicit representations. So all of that is happening online. The final meshing is something that we would still perform offline, but during the actual trajectory, we can achieve real-time training of implicit representations. Let's see. So the feature that allows us to achieve this real-time training is that we have an adaptive loss function that is kind of leveraging uncertainty in each learned region to focus on certain regions more than it focuses on other regions, right? So regions that it learns well really quickly, we're going to ignore those, and other regions we're going to keep refining. So I think this adaptive approach and this kind of uncertainty-aware approach can be really useful when we move from offline training to online training, right? We need to start to encode some extra information about our scene, and we need to be able to adapt to these different scenarios to focus on what is most important for actually achieving our goal outcome. So once we have our learned implicit representation, we can render from novel viewpoints. So this is just carrying out a new trajectory and demonstrating that we can reconstruct some pretty complex image spaces with pretty dense reconstructions. So the scene, has a lot of transparent surfaces, a lot of thin features, and we're able to get pretty good reconstruction of those. Again, learning this representation online. And then one more example, maybe a little bit with more natural features like trees and plants. I think this data set had mostly indoor, outdoor courtyard scenes. you can see for these tree features, we're able to make out pretty high resolution, dense reconstructions of pretty fine features as well.
So how does it deal with, so these were glass environments, some of them, right?
Mm-hmm.
So directly scan is going through. So how does it deal with that right now?
Yeah, so one thing I've noticed in working with NERFs is they're pretty good at denoising. So if you have, a few returns from sequential scans, it's pretty good at learning what is noise and what is not noise. And we've seen this for LiDAR, but also for multi-sensor fusion. So I think that's something that's a really nice advantage of working with these representations. Yeah. It's kind of a natural thing that we get out of it. Okay, so with this, we're able to perform online SLAM with implicit neural representations, and we had no RGB information, so this is something that we're working on currently, is kind of combining the power of both LiDAR and RGB, but still enabling real-time SLAM. Okay, so lastly, I wanted to talk about a third application that I worked with a bit during my postdoc at Georgia Tech. And this is space robotics. So I think space robotics brings up a really interesting challenge for machine learning, in that it really requires machine learning models that we train, on land or in simulation to be generalizable to new scenes. And I think this is an open challenge, but one thing that I find really interesting. I think one of the first steps is really to think about what causes this breakdown in generalizability, or what axes we need to improve our generalizability to. So what inspired this initially was I had one of the first projects I worked on as a postdoc was visual SLAM for asteroid relative navigation. So we had essentially an orb SLAM pipeline that we modified to work pretty well for asteroid relative navigation, where we have images of the camera orbiting the asteroid. We're assuming a fixed frame for the asteroid, and we can get a reconstruction of the asteroid and localization of our camera around it. And this is real imagery from the PDS database from NASA of a real asteroid mission, which is all publicly available. So one thing we found in our experiments with this visual SLAM pipeline is that there are some challenges with working with traditional feature-based approaches for problems like this. So asteroid imagery is pretty interesting, or space imagery is pretty interesting because you have this large light variation as you move from one perspective to another, and you can have really extreme shadowing effects. So it can be challenging for traditional feature-based approaches. Current state of practice is to use DTMs, digital terrain models, which require a lot of human oversight to make sure that there's good alignment from feature to feature. And we were interested in seeing if deep learning could help us overcome this challenge or improve our feature detection frameworks. Unfortunately, there weren't really any available benchmark datasets at this time that we worked on this project. So we looked into developing a dataset or compiling a dataset that we could use for training deep learning for feature detection. So this was called Astrovision, and a lot of this work was with Travis Driver, who recently graduated from Georgia Tech. So for this work, we compiled the Astrovision dataset, and it leverages publicly available images and 3D models from NASA's Planetary Data System, PDS, of many different asteroid missions of different asteroid shapes and types. And we compiled both the images and the 3D models, and we used the 3D models and the image positions to basically create synthetic depth maps from the 3D models to match with the corresponding images. This allowed us to find ground truth feature correspondences from one image to the next, and we used this for creating a training data set for training feature detection. So we need both the input images and the ground truth feature correspondences for training these networks. So we trained a network, one called ASL Feet. We tested a lot of different frameworks, and we evaluated training on terrestrial data sets, so data sets that were already publicly available, and the Astrovision data set that we had essentially compiled and computed the ground truth for. And we found that, in general, being able to train on asteroid images is much more effective than training on terrestrial data sets that are available. Being able to actually, train on data that matches the features that you're expecting to see is really important. And we had a couple of really interesting insights from this work. So one is on the top row, that's images trained on terrestrial data. And what you're seeing is kind of where the network highlighted important features to look at. And you can see that for training on terrestrial data, what it was looking at, it often caught kind of the edges of asteroids where you drop off into space, and you have this really large contrast. Of course, those features aren't very meaningful because as you move around the asteroid, if you're only capturing the edges of the asteroid, you're not going to be able to match any features. When you train on asteroid imagery that has similar features, the network actually pays much more attention to the features on the surface of the asteroid for finding feature correspondences. So it's actually looking at the surface of the asteroid, which is much more informative for the problem of feature detection and matching on asteroid surfaces. We also looked at training and testing on different perspective changes. So you can see training on terrestrial data on the top with large perspective change. It has challenges finding feature correspondences, but training on astrovisions or asteroid data set, even with large perspective changes, we can slightly improve our performance for feature detection and matching. And we saw this across a couple of different types of asteroids as well, so that's what you're seeing on the bottom. But I also want to point out that, again, this could still see some improvement, right? So maybe one area for improvement. We also tested varying illumination, and I would say this is even more challenging than the perspective problem. If we have really large changes in illumination from one image to the other that we're trying to match, which happens, frequently when we're moving around these objects that have really extreme changes of lighting conditions, then this is another challenging place for training and testing feature detection methods, especially when you have asteroids of complex objects. So I would say the asteroid on the bottom is a bit more regular shaped, maybe fewer shadowing effects, and the asteroid on the top has many more extreme shadowing effects as well. So this just taught us a lot about the need to think about what the open challenges are. If you're going to think about deploying deep learning in an application like space robotics, we really need to think a lot about what our training data is going to look like and how that's going to impact our performance at test time if we're going to see these really large changes in illumination or perspective change at test time. So the last problem I want to talk about is a problem on autonomous landing on planetary surfaces. So here we were looking at training deep learning models for detecting safe and unsafe landing sites. So again, we have the challenge that we don't have a lot of training data to be able to carry this out. For this work, we leverage simulated data for training and testing for our method. But what we were thinking about here is, okay, we know that our training data isn't going to be perfect, right? At test time, because we're going to a new environment, we might see things like different terrain than we trained for or different sensor noise than we trained for. And how can we actually overcome that in practice if we're going to try to deploy these deep learning models? So what we were interested in is if we could develop uncertainty-aware deep learning methods to help us interpret essentially the prediction from our deep learning model for a practical application of safe landing site selection, where safety is really important. So for this work, we used the Bayesian SegNet, which already existed, but we trained it to perform safe landing site selection, where we're taking in an input digital elevation map and outputting both the network prediction of safe and unsafe, and also the uncertainty. So for Bayesian SegNet, during training, it's only outputting network prediction, and that's based on the label that we're giving it. But then during testing, it outputs both network prediction and an uncertainty map. And this works by using MC dropout. It uses dropout layers at test time. We perform, I think, 8 forward passes with the same input at test time, and then we evaluate the statistics of that. So There are multiple ways to get or estimate uncertainty depending on the type of uncertainty that you're looking at for deep learning models. We chose to use the entropy of the predictive distribution because this can capture different types of uncertainty in our test time. So for our experimental setup, again, we had simulated data for this because it's difficult to get access to real data for this problem. So we developed a Mars terrain simulator, and from this we could output these DEM maps, the digital elevation maps, and we specifically were looking at the case where we had one sensor noise parameter at training time and different sensor noise parameters at test time to see how we could overcome this. And with our output, again, we get the initial network prediction and the uncertainty map. We found an uncertainty threshold for thresholding whether we were certain enough, and then we thresholded our network prediction to only account for areas where we were both certain and accurate to consider for our safe landing site selection. So a couple of notes on this uncertainty threshold because it's really important. For us, we used the mean uncertainty value across the validation set, but it's really important which threshold you select depending on your application, right? And I think this is an area that is really interesting for future work as well, that if you set a conservative threshold, you're going to end up with, more sites that are accurate and certain, but maybe fewer sites that you can actually consider for landing. Whereas if you're not conservative, you have more sites that you can consider for landing, but you might have some of these bad cases where you think you're certain about that site, but it's actually inaccurate. It's actually unsafe for landing. So we were able to find a threshold that worked pretty well across different sites, but I think this is one thing that's really interesting to consider for the future is that some of these decisions might be task dependent, right, and dependent on our risk acceptance. So for some results, if we see at the top, we train and test on the low noise case. So we have the same noise at training and testing. Our uncertainty map looks pretty good. So we're pretty certain about the prediction that we have, and we're able to consider a lot of spaces for safe landing site detection. On the bottom, we trained on low noise scenario, but then at test time assumed that we had much higher sensor noise than our training. And this is, you can see, leads to a much different network prediction. And if we were to use that network prediction outright, then we would have a lot of error in that safety map that we're using. But we can find some useful information from the uncertainty map if we're estimating uncertainty as well. And thresholding on the uncertainty map allows us to actually find a safe final landing site to consider that we are more certain is accurate in the end. So this is kind of an overview of some of the challenges that I've worked on for machine learning for perception for field robotics and things that I think are kind of still open challenges and maybe interesting areas to think about for the future. But hopefully that gave you a good span of the applications across field robotics and some of the perception challenges that we face. So I just want to make some acknowledgments because many of these projects feature very large teams, right? In field robotics, we're deploying hardware in challenging environments. So a lot of this work was carried out in collaborative projects, both at Georgia Tech and at University of Michigan, with my collaborators at Louisiana State and Michigan Tech as well for the Thunder Bay work. But I think we'll have a couple minutes for questions, but thank you very much for listening.
Thank you, Katie. Any questions for Professor Skinner?
In the context of the real-time neural-based reconstructions, I guess what was sort of was the keyframe selection, or sort of what's the key idea that gets you to real-time with that?
I think the main thing is that adaptive loss function. So the tracking and keyframe selection, we're kind of using traditional SLAM frameworks there. It's really just for the mapping component that we're using the implicit representations. So yeah, it's really just trying to reconfigure the loss function so that you are, not focusing your training across the entire scene because that will take a long time, but try to figure out what's important for the training process.
So as a follow-up to the question about the uncertainty for the light on Earth, when you focus on scenes or areas where you had more uncertainty, did you see any negative effects on focusing on those scenes as compared to the ones that you learned quickly?
That's a good question. I think that there was a bit of tuning involved with figuring out how much, I guess, leniency to give it. So I'm not sure exactly, so I might need to refer you to the paper, but I think there was some design choice there as well of how much you focused on, one region over the other.
Could you walk through that adaptive loss function a little bit in more detail there? Like, how did you prioritize the fact that certain parts of the image weren't characterized well and others were?
Let's see if I can go back here. So we used the JS divergence function for the loss. There had been work looking at KL divergence as well, but we found better results with the JS divergence. Let's see if I can get back here. So it's really when it's looking at, I think these were the previous methods, used kind of a uniform margin for training the range measurement. Our method is able to adapt that margin that it considers for training the range measurement for either newly observed regions or previously observed regions that it's seen. So, but the paper is on archive as well if you need more details. One more question?
I had a question regarding water nerve. So the original nerve idea is they assume like the light is traveling in a straight line, but underwater I'm assuming there would be some bending. So how do you deal with that in water nerve?
Oh, do you mean
like some refraction or something like that?
Oh, so refraction, so we're calibrating our cameras underwater, which isn't perfect. We're still using the pinhole camera model, but that can help reduce a lot of error from refraction. So that's one thing that we're doing to handle refraction. We're not explicitly modeling that in water nerve.
In the water nerve, is the occlusion heterogeneous, or is it sort of uniform? Is the attenuation sort of?
We assume that it's uniform across the scene. Yeah, so that was one of kind of the first works on using deep learning for image restoration. So kind of one of the constraints that we made to make it work. So yeah, I think more recently there's works that look at generalizability to different environments, or even kind of in local environments, you can see a much different effect. Yeah. Oh, sorry.
Was there a reason? So the last bit that you presented on using Bayesian deep learning models for predicting safe landing sites. So was there a reason for choosing Bayesian approach versus the other stuff that you showed had machine learning components? But what was the reason for using Bayesian deep learning models in this case?
We tried a couple of different methods, and this one seemed to work pretty well. I would say the one downside is you are still doing multiple forward passes at test time. So for something where you needed real-time output, that might not work well to use this Bayesian segnet method. But for safe landing site detection, you can have longer time. You don't need to be operating at 30 frames per second to output that. So that might be one thing to consider if you're looking at other methods. Yeah.
Just one minor question. So you mentioned you guys made your own simulator for the segmentation data set.
Yeah.
Have you considered using like HoloOcean, or did you try other simulators, or did you find that they were like they couldn't give you what you wanted for that project?
So for us, we were looking at pretty specific scene type, I would say, in that we wanted to look at shipwrecks. I think there's one shipwreck in HoloOcean, but we needed a lot of different variation in how those shipwrecks appeared. So it was just a little bit easier for us to do the scene generation programmatically to be able to just drop 3D models in. And we didn't need as much the rest of the context that I think Hollow Ocean provides, but for different sensor types like forward-looking sonars, I think that's a really great tool.
A few years ago, the Chinese managed to land on the dark side of the moon. Afterwards, the Russians tried and they failed. Then the Japanese tried and they failed. Then the Indians tried and they were successful. So this is like 50% success. In your opinion, what is it that makes this problem so difficult?
Oh, I can't speak to all of the operational challenges there, but I think on the vision side, low light is still a huge challenging domain for us. And I think one thing is moving away from cameras or looking at multimodal perception could be really important in some of these environments, right? To not just rely on vision in these cases where we know vision is going to be poor. So I think, maybe that could be one thing that could help. But I'm sure there are many other challenges that they encounter.
Let's thank Professor Skinner again.